Here is the parametric condition of the circuit with no field engaged. We're going to try to do it quickly in this video to show the phenomenal efficiency of the resonant coil system to ignite a small neon bulb. Right now we don't have anything going. We haven't engaged the field. Those are the circumstances we see before the field's engaged. It's from rotational magnetism. Over here we have some past statements. The phase angle between two or more sources is not exclusively determined by the source, but also by the load it serves. We're going to try to show how this considerably varies in the lighting of that neon. Down here we have the circuit, and the law of cosines that we use by voltage meter readings to determine the acting phase angle. On this circuit, we have switches that connect to the capacities that the secondaries use. Secondaries are the two coils there. And the respective voltages on each of them front and back coils. And this is the power system that we use for the wireless Tesla coil that shoots that 1 volt up to 340 some volts at the arc gap. So that's a 340 to 1 voltage transformation. And that voltage transformation is made by collectively wiring two secondaries together, whereby there's only two ways to wire them, either for or against the voltage that you're going to receive, and thereby we determine that phase angle by that equation. Also, we have a scoping on the second coil, what I call the gate circuit. And right now you can see it's at the 0.2 milliseconds per division, and that shows us 1 cycle of the alternator. And on the 666 machine, it's actually like a clock with, instead of 12 numbers, there's 24 numbers. And the signal recombines on the 1/6 interaction to create every 24 cycles a revolving voltage in time. Now we're going to turn the sweep rate up and show the effect right now of that revolving voltage in time. We're going to increase the sweep rate tenfold from 2.2 milliseconds per division. This is at 0.5 volts per division. And we will then see the effect in time itself of the cycle of how this reaction, third secondary magnetic reaction works. So we're at 0.2, 0.5, 0.1, 2, 5. 5 milliseconds per division, we can see the influence of the time. Further at 10, and finally best at 20. This is a good scope where we can record these things. So we got a pretty good signature there at 20 milliseconds per division. And when we make these changes, we'll be able to see how this revolving, right now the revolving voltage in time is pretty much acting in a maximum manner, and at one point it's completely blocking the primary's magnetic field from entering that secondary. We have two influences here, not just the primary to secondary, but there's a third secondary to secondary action that we're going to see right away here that determines why and how these things act. So now try to finish out here. We're going to go back here and look at our relative voltages of each item. We have the 158, the 204, and the 342. There's 342 volts across that neon. The neon is not lighting. Now what we're going to do is we're going to disconnect on that switch V2. Then we're going to disconnect the V1. And then we're going to look at the new phase angle created just from the reactances. Right now that phase angle would appear to be over 120 degrees. Typically we measure it at 135 or so. That can be put on the video as a calculation later. I'm going to have to walk across front of the camera and show the relative differences now. Go back to the scopings. Shutting off V2. V2 powers V1 in reverse phase rotation. What's going on? Well, that's the wrong wire, folks. Sorry about that. So now we only got 15 volts on V2, and V1 is decreased to 171 volts. Now we're going to disconnect V1. Now we see that we got 22 volts, 18 volts, and 19 volts between them. Quantities are almost all equal. That's an equilateral triangle. By the law of cosines, we know that angle is around 60 degrees. So when we look at the situation reactively, 60 degrees. But when we look at it resonantly, it's over 130-some degrees. Now we've established all that. What we're going to do now is turn the field up. Have time to show the difference in scopings and show the scoping and the reactive scoping difference. Now the revolving vector in time barely has any influence. The revolving vector in time only has influence when we draw from the source, and when we just seen when we draw from the source, we change our phase angle observation, etc. on down the line. In other experiments we can show that there is a 15-degree contraction of time measured from the system without disturbing the system by having loads. And for now we're going to try to get on there, and we're going to go in there and turn the voltage source up to its smallest level that we use is 7 volts. Okay, walking against the camera again. You can see now that our level here, we've got 116 volts before we make anything resonant. We've got 129 volts, and we got 106 volts in the back coil. And our inputs accordingly. We're only really working at a 5 volt some level. And all them phases 1, 2, 3, and 1, 2. Stator voltages are on top. Phase amperes are on bottom on chronological order. Looks like our scoping went off the rail. We should turn that down. That's all the way up to the very top, 5 volts per division. Well, we increased everything 5-fold by the stator voltage. We can see that. So we ought to expect the scope signal to increase. Now let's get to the dirty work here of showing our neon bulb ignition. And to do this, we want to disconnect all our voltage meters and then reconnect the circuit. Just for a safety measure, record all the amperage. And we're going to see when we oh no, we're going to have to do something else. There's only one side hooked up. The other side up. Now hook the meters back up. This should be a dangerously high level. All the meters. 655 volts. We can't keep this going on. 600 volts. And a phenomenal. I say a phenomenal. 129 volts across that bulb. From this information, we can form a phase angle, and we can also calculate the current or predict the current across that bulb. So I think we've done enough for this first video of 2014 to show some remarkable things about this resonant voltage system. Thank you.